this is a redox reaction, reduction and oxidation. So oxidation will take place at one electrode and reduction at the other. And this is true for most of our batteries. A battery is a means of storing electrical energy. This is a single cell. Battery literally means a bunch of cells together. So batteries obviously are quite crucial. You probably charged your phone, possibly your watch, possibly your wireless earbuds, and a whole bunch of other devices for the day, probably overnight, and batteries are quite crucial. The technology is getting better. They will take more cycles and more charge and contain more energy for less mass. That's particularly important for electric vehicles. So electric cars are increasingly taking up but need a bit more time. Electric motorbikes I'm very, very excited about because they have ridiculous amounts of torque from zero, but the batteries are too heavy at this stage. But we're going right back to the start of batteries. So the very first cells, Alessandro Volta in Italy did some work on batteries and cells. Alessandro Volta used to like to get frogs' legs that had been removed from the frogs and put electrodes on them and make them jump and things like that. And Luigi Galvani, the Galvanic Cell is named after Luigi Galvani, who discovered some of the very first batteries and cells. So this is a simple galvanic cell. We're going to take some copper sulfate solution, so that characteristic blue colour of copper, and put it in one of our beakers. I'm wearing gloves. None of these are particularly nasty. Copper sulfate is not great, but it takes a fair bit of it to harm you, but it's good practice to make sure that we're wearing the appropriate protective equipment. Zinc sulfate is going into the other beaker. So I might top up the copper just a tad more as well. So we're going to have a copper 2+ half reaction in one of our cells. So I'm going to put also an electrode of copper metal into the copper solution. So it's Cu2+ reaction that's being driven by the cell, and in the other Zn2+. So a zinc and zinc ions. So we've got zinc ions in solution, we've got the sulfate in both cases, but it's basically zinc ions floating around and sulfate ions, copper ions and sulfate ions. Now we nearly have a cell. We have two electrodes. We can connect our voltmeter to them. We've put the voltmeter on the 2000 milliamp scale, so we should read a number of milliamps, which are thousandths of amps. Now, I'm not seeing a voltage reading yet. And if you take your chemistry brain off and put your physics brain on for a minute, you'll see that we've got a circuit. The current can flow from one electrode out through the resistor and back around the wire to the other electrode. But hang on, there's a gap here. Our circuit isn't complete. So what will happen is electrons will build up in one place and you'll have a concentration of negative charge, and that will repel any further electrons, so the process stops. Similarly, on the other place, you'll have depleted it of electrons, it'll have a positive charge, it will repel any further positive charge. So what we need is a salt bridge. A salt bridge just has ions of some third substance in it that allows the circuit to be complete. And when I complete the circuit, we should see a reading on the voltmeter. So I'm going to soak, this is a piece of filter paper that we've cut to shape, and we're soaking it in concentrated sodium chloride solution. So it's just common table salt, it's saturated solution, so it's very concentrated. It just means there are lots of sodium ions and lots of chloride ions ready to actually carry charge between the two. So then we use that as a bridge across between the two cells, submerge it in both, and you can see the voltmeter reading increases straight away. It's about 22, 23. It's going to take a moment to equilibrate. It seems to be settling at about 25 millivolts. Now that's less than we would expect. We'd expect for this particular reaction, the two half reactions, the copper and the zinc, we'd expect a reading of 1.1 volts. I suspect the issue is some of our wiring is fairly hinky. We could make that a fair bit more electrically accurate, but I suspect the key issue is the salt bridge, that the ions are not able to move through our filter paper salt bridge as quickly as perhaps they could if we had a glass salt bridge with stoppers in the ends. There are a whole variety of different salt bridges that you can build that allow the ions to just move that little bit quicker, and therefore to get a current moving in the circuit, because you're not going to get a voltage across that resistor until you've got a current flowing around the circuit. But nonetheless, we've seen the voltage that's been produced by our galvanic cell. We can analyze and understand what the potential voltage should be, and basically every system in the universe is less than 100% efficient. In every system there is some loss to, for example, resistance in the wires and the various other elements that are going on, but we have seen the galvanic cell. Hopefully just a very quick calculation for the galvanic cell, because I think I mentioned in the video that the cell potential for our cell, which had a copper and a zinc electrode, was 1.1 volts. So I just want to demonstrate where that number comes from effectively. So in this case we had a Cu2 plus ion, so that has a particular half potential, and we had a Zn2 plus ion. If we check the cell potentials for those, let me rewrite those as the full equations, because it'll be just clearer where the electrons play. So if we write down Zn2 plus in aqueous solution plus 2 electrons gives solid zinc, Zns, Cu2 plus in solution plus 2 electrons. We've written them down both in the same direction, gives copper solid. Now one of those equations or reactions is going to be driven forward and the other backward by the redox that's happening. So the cell potential for this one is minus 0.76 volts. The cell potential for this one is plus 0.34 volts. So basically what ends up happening is that one of those, as I say, is driven backward by the other. The one with the more negative sign, sorry, that shouldn't be a 3, it should be a 7. The 7 was so broken it looked like a 3, and then I followed it. Right, will be flipped. So basically the overall cell potential, because these are called half cell potentials, but the overall cell potential is made up of an oxidation potential, which is one of these reactions being oxidized and the other being reduced. So write potential in both of those cases, not spelling it amazingly. And as it turns out, the one with the more negative or less positive reduction potential in the half cell will be flipped. So basically what we'll end up with is this zinc one going in the opposite direction. So Zn, this will be the oxidation reaction. Zinc metal going into solution, off the electrode into solution, as zinc 2 plus ions and giving up electrons. Those electrons then travel around the circuit and allow copper to come out of solution onto the copper electrode. So that's the direction it's going to drive. And when you flip the direction of the reaction, that's going to be plus 0.76 volt. So this one ends up being the oxidation. We use the little acronym, I don't know whether you've heard this one, but Leo goes GER, GER, G-E-R, not G-R-R. So Leo goes Ger means lose electrons oxidation, gain electrons reduction. So the zinc, in this case, is losing electrons. They're going away from it to make it into ions. So it's the thing oxidized, and the copper is gaining electrons. So you're going from copper 2 plus 2 electrons to form copper solid. So it's gaining electrons, it's the thing reduced. So we add the potentials of both of those. This one is still going to be in this direction, Cu2 plus, I won't bother about putting in the aqueuses in this case, plus 2 electrons gives copper metal, and because it hasn't been reversed, its potential stays the same, 0.34 volt, and if you add those up you find 1.10 volt. So that's the theoretical potential of our cell. We actually found in our experiment a result of 25 millivolt, which is 0.0025 volt. So obviously a lot smaller than the theoretical result. As I mentioned in the video, I think the salt bridge was probably the culprit, but certainly in your write-up you can talk about the theoretical potential of that cell and why we didn't recognize our potential in this particular experiment.